2.2 calories per gram Celsius. So now I drop this from 50 meters high, and let's say the mass is 2 kilograms. So let's say there is air friction, and that 10% of its potential energy is converted into heat. So let's say the initial temperature of the block is 20 Celsius. Okay, so this is a good problem.
That's what I was going to ask you about the, I was going to ask you about the converted into heat. It's because the air is cooling the object, or possibly?
Well, usually when you have frictional losses, let's say you drag something along the block, let's say a block along the table, you're producing heat. Friction, the work done by friction goes into the heating the object. So in the case of falling through the air, right, as the air drag is happening, what's going to happen? The block is going to heat up a bit. Usually when we do these kind of problems in physics 1, in mechanics, we're assuming there's no air friction.
Yeah.
And then the question is asking, what's the final velocity?
So right? Then it could kind of be like the molecules in the air are bumping into...
exactly. They're bumping into the copper, and the molecules of the copper are starting to get agitated.
Got it. Okay.
Yeah. So its potential energy is not completely conserved, and it doesn't completely go into kinetic energy, right? That's why when it finally falls to the ground, its kinetic energy is less than it's supposed to be.
Got it.
And the object is a bit hotter. So when it hits your head, right, it's not only going to be going fast, but it's going to be hotter. Right? So what is its final temperature? So this is a good problem because it utilizes some physics concepts from Physics 101, right? So the potential energy initial is mgh right? 2 times 9.8 times 50. What does that give you? Well, that's pretty easy, right? 100 times 9.8, 980 joules. Okay, if 10% of that is wasted to heat, so 90% of it gets converted into kinetic energy. So kinetic energy final is equal to 90% of 980. You see that? So final kinetic energy is 90% of 980. And that's equal to 1/2 times its mass times V final squared. Okay, so then okay, that's it. You just multiply those out.
How do we know that we're supposed to use 0.9?
Well, I'm going off the fact that 10% of the energy is lost to heat. Good
Oh, so
question.
we have 0.9 left. Okay.
Yeah, and then there's 0.9 left. Good question. Any other questions?
And Professor, could we explain again why you put equal to 1/2 mv squares?
That's the kinetic energy.
Kinetic.
Remember the equation for kinetic energy?
Yes, for last one.
Yeah. So I'm setting the kinetic energy, the final kinetic energy of the object, to 90% of its potential energy, because 10% of it is lost.
Yes.
Okay, now the rest of it, how do we find the final temperature? What should we do?
Oh, but I think what his question was, Professor, was that I guess once it's moving, because the potential energy is when it's stationary at 50 meters above, and then
Yeah.
Once it starts moving, then you go into the kinetic energy equation.
Yeah, so at the end, I should have drawn a better picture. At the end, we have the kinetic energy.
Yeah.
Right? Final. And then the potential energy final is 0.
Yes. Yeah, I think that's what he was.
Yeah.
Thank you.
Yep. Okay, now the other one, to do the temperature, I'm going to say H equals mc delta T. So how much heat will go into heating the object? 10% of 980, right? So 10% of 980 is actually what's heating the object, right? And so now here, let's be careful about units. This is joules. And then the mass is 2 kilogram. And then specific heat, we're given the specific heat in units of calories per gram. You see? So be able to be versatile. If this is if the units are given in that, 0.092 calories per gram Celsius. Okay, so write that down. So you see, H is joules, mass is kilograms, 0.092 calories per gram per Celsius. So then I need to say 1 calorie is 4.184 joules. Okay, and then that joule will cancel with this joule. And then, of course, the calorie will cancel that calorie. And, I want because I need delta T here, right? So I need this gram to cancel the kilogram. So I could say it this way, I guess. I could change this to 2,000 grams, right? 2,000 grams. So this is where a little bit of unit analysis, which you do a lot of that in chemistry. So it comes in really handy here. 2,000 gram. So gram cancels the gram. So 2,000.092, this guy, this guy, this guy. Now everything is gone. So now the only thing left is the Celsius. So when we calculate delta T, the Celsius goes up over there, cross multiplies, and gives you the answer in Celsius. So let's see what that is. Not too much, huh? So imagine this is copper, which is actually, copper is actually easy to heat. 0.092. Actually, copper is not one of the really, really easy ones, 0.092. That's almost, no, it's still pretty easy. So it didn't actually heat up too much. So the final temperature is gonna be the initial temperature plus this. So 20.127. The aluminum is falling. And then there's water here. Oh, sorry, this is copper. Water. I believe specific heat of aluminum, it's one that I've memorized. 0.215 calories per gram. Okay, so let's say same problem, but now I'm adding a different part to it. I'm saying you're dropping the copper block, and over there on the bottom, there's water in thermal equilibrium in an aluminum can. So they're both 5 Celsius. The mass of the water is 200 grams. The mass of the aluminum can is 40 grams. The specific heat of aluminum, 2.215 calorie per gram. Specific heat of water, 1 calorie per gram. And this copper block falls into it. So what's the final temperature of this mixture with the copper together with the water and the can? So now it became a really good problem because you have to do the first part of it correctly, right? You have to do the first part of it correctly. You have to get the temperature of the copper. Then once you get that, you're not done. Now you do a calorimetry problem.